Welcome back to Advent of Code 2024, day 17. So, all right. Oops. Hello, Forest Opus. Welcome in. Okay. Day 17. Let's go. Day 17. Chronospatial Computer. The historians push the button on their strange device, but this time you all just feel like you're falling. Okay, don't really remember this. Situation critical, the device announces in a familiar voice. Bootstrapping process failed, initializing debugger. The small handheld device suddenly unfolds into an entire computer. The historians look around nervously before one of them tosses it to you. This seems to be a 3-bit computer. Its program is a list of 3-bit numbers, 0 through 7, like 0, 1, 2, 3. The computer also has 3 registers named A, B, and C, but these registers aren't limited to 3 bits and could instead hold any integer. Okay. The computer knows 8 instructions. Here we go. It's all, it's int code stuff. Each identified by a 3-bit number called the instruction's opcode. Each instruction also reads the 3-bit number after it as an input. This is called its operand. A number called the instruction pointer identifies the position in the program from which the next opcode will be read. It starts at 0, pointing at the first 3-bit number in the program. Except for jump instructions, the instruction pointer increases by 2 after each instruction is processed. I've always liked these emulator problems. Yeah, they're pretty good. What was it, 2019, where the one was the one which every other problem was int code. I think a lot of people out there, there were very mixed reviews of that. I think a lot of people got completely burned out. And I can understand it's quite quite tough when you actually need to keep developing your program between problems and you can't just do the later ones independently. If the computer tries to read an opcode past the end of the program, it instead halts. So the program 0, 1, 2, 3 would run the instruction whose opcode is 0, pass it the operand 1, then run the instruction having opcode 2, pass it 3. Okay, fine. There are two types of operands. Each instruction specifies the type of its operand. The value of a literal operand is the operand itself. For example, the value of the literal operand 7 is the number of 7. The value of a combo operand could be found as follows. Combo operand 0 through 3 represent literal values 0 through 3. 4 is A, 5 is B, 6 is C, 7 is reserved. Okay. The instructions. 8 instructions. Adv is division. So it's A divided by 2 to the power of the combo operand, right? All right, fine. BXL is bitwise XOR of B and the literal operand. Okay. BST combo operand modulo 8 written to B. Alright. J and Z does nothing if the A registers. Okay. I don't just skim through these. Might as well just code them as I'm properly reading them. Alright, seems straightforward. The historian's strange device has finished initializing its debugger and is displaying some information about the program it is trying to run. Your puzzle input, for example. Alright. Your first task is to determine what the program is trying to output. Oh, it's going to be like a more investigative one. To do this, initialize the registers to the given values, then run the given program, collecting any output produced by out instructions. Oh, okay, we just output the answer. I thought we would have to set values to make a certain thing happen or something. Okay. Fine. Should be able to do that. Alright. Alright, so I guess we want... Okay, just extract. So I guess A equals int f dot read line dot split. Just take the last thing there. I suppose we can just do that. Yeah. B and C. And then just take in a line. And then we've got the program, so it's going to be that final token. So program equals, so that int, so it's going to be int x for x in dot split on commas. Okay, let's just check this. A, B, C, program. Okay. So now we want does anything affect the instruction pointer? Don't see anything. J and Z. Oh. Oh yeah, of course. Jump. Fine. Alright, so I guess we'll make a method. Define. So, okay, so let me just take a look at these instructions. So they're generally going to write stuff to A, B, and C. Alright, we'll allow this function access to so if you run an instruction with a opcode and an operand, we are giving instruction pointer A, B, and C, giving it access to those. Let's say IP equals 0. Alright. Now we just do a big if else. Let's see. If opcode is 0, so this is division. The numerator is the value in the A register. The denominator is 2 to the power of the combo operand. Literal operand is the operand itself. Combo operand. Okay, let's make a little combo operand sub-method. If so, it's 0 less than or equal to operand. It's less than or equal to 3. Return operand. Elif operand is 4. Return A. B. Operand equals 6. Return C. 7 is not going to come up. I'm guessing 7 might be used in part 2 or something. Okay. So if opcode equals 0, we're doing okay, so it's A divided by truncated to an integer. Okay, so it's A divided by 2 to the power of the combo operand. All right, so A divided by 2 to the power of get combo operand. Don't need brackets, just do it anyway. And that gets written to A. All right, opcode 1. So this one, let's just mark these. That's adv. BXL. Bitwise XOR of B and the literal operand. Okay. So it's going to be B equals B. I forgot what XOR is. Is it this? I've got to double check that. Yeah, okay. B equals B, XOR, and we just take the literal operand. All right, these individually are quite simple arithmetic operations. All right, so BST. Combo operand modulo 8 written to B. Okay. J and Z. So if A is 0, we do nothing. If it's not 0, jumps by setting the instruction pointer to the value of its literal operand. And we don't increase the instruction pointer by 2. So every other one of these increases instruction pointer by 2. Okay. Fine. Alright, we'll just do, just at the end here, IP plus equal to. I guess we can compensate. Oh, it's a bit. Okay, we'll do it this way. We'll compensate by saying IP equals operand minus 2. It's not really the best way to do it. Really, we should actually just be adding 2 to every valid thing. Alright. Anyway, elif opcode equals 4. So B equals BXC. B equals B XOR C. Doesn't use the operand. Okay. If opcode equals 5, this is out. Outputs that value. I guess we also want an output. Just make that a list. So that's not. Just put this at the top here so I remember. Okay. So combo operand modulo 8 and outputs the value. So output dot append get combo operand modulo 8. BDV. It's adv, but we store the result in B. Okay. And then 7. CDV. It's adv, but we store it in C. Alright, fine. Alright. So general use is so they said while IP is between 0 and length of program, opcode, operand, so would we ever have the situation where it's pointing at the last thing, in which case there would be no, it would be invalid because there would be no operand? Do we need to check for that? If it tries to read an opcode past the end of the program, it halts. But it doesn't say anything about the operand. So I just hope that doesn't come up. Doesn't happen, yeah. Seems like that's not a case you're supposed to handle. Alright. So opcode operand equals program IP. Program IP plus 1. So we run instruction opcode operand. That's it. And then print comma dot join string x for x in output. Run. How long is this going to take? It's a short program, but it's already taking a while. I think it might be stuck in a loop. While IP... Am I definitely modifying this IP? It should be. No, stop it. Let's just print IP A B C. It's stuck in a loop. Okay. Yeah. Let's make sure I've got... Did we ever get any output? We're just forever adding ones. Yeah, that's not right. Okay. I guess we have to, Okay, I'll have a quick check of this and then I'll try to run it step by step and see what's failing. let's make sure each of these is correct. So combo 0 to 3. 4 is A, 5 is B, 6 is C. Okay. And then opcodes, we've got 0. Make sure this one is correct because we've copied it 3 times. So we've got A, integer divide, 2 to the power of the combo operand. And then written to A. Yeah. Okay. Okay, so code 1, B equals B XOR operand, upcode 2, BST. B equals combo modulo 8. Yeah. The jump could be a bit funny. IP equals oh, I didn't even do the 0 check. Damn it. If A not equal to 0. All right. That looks like something. Correct. Alright, part 2. Digging deeper in the device's manual, you discover the problem. This program is supposed to output another copy of the program. Unfortunately, the value in register A seems to have been corrupted. You'll need to find a new value to which you can initialize register A so that the program's output instructions produce an exact copy of the program itself. Ooh, okay. $117,000. What is the lowest positive initial value for register A that causes the program to output a copy of itself? Okay. I guess we just loop through values of A. Yeah, we'll try looping through A and see if I can't imagine there's any real. It's not like we have to really work out what this code is doing, do we? That's usually really tough. Right, we'll try just looping through values of A then. So, let's define let's modify this. Say define get output for given given IP A, B, C. All right. Yeah, okay, so we just start I'm just trying to think how I want to. All right, okay, so we just break as soon as we see that the output is not matching. That'll probably save us a lot of time. So reinitialize. These, I suppose. All right, just reinitialize everything. All right, we'll just do it for A in count forever. Positive initial value. Okay, so it has to be positive. So count 1. We initialize IP equals 0. B, C equals 0, 0. Output is clear. We run. Let's just say outputs index equals 0, because I want to be comparing with the program. All right, so we're just going to run this. As we did before. Okay, we just do that. And if okay, after we've run an instruction, just check if we've output something. So if length output is greater than output x, that means we've output something in that instruction. We just want to check that it matches program. So if all right, let's just wrap this all up as a method. Define get lowest A if we don't need this as a method, just get rid of that. If output put my x is not equal to program, or if length output is greater than length program, so we've exceeded. Then that means we just break out of this loop. This is a fail. Otherwise, we're still in line with program, so we can say just say output ix plus equal 1 to keep up. So if we get here, so we break out of that. If we get here and output is identical to... We don't really need this step, but then there are some values of a which might loop or make massive things, so yeah, we probably do need this step. Alright, so just say, oh man, there's going to be some a's that loop infinitely, maybe. We might need to use states to check if we've repeated a state. Oh, there's almost certainly going to be something like that, isn't there? Alright, we'll try this anyway. If tuple output is the same as tuple program, what did they want? The a value, okay. Print a. No, we want the initial value. Break out of this. Alright. Let's try this. Also, let's say print if a percent unit percent 100 equals 0. So I want to see what speed we're getting here, if it even gets that high. Okay, we're not getting any infinite loops. That's good. Probably costing a lot of time printing. We're at like 20 million. Printing too much. Can go like every 100,000, but I guess I'll just leave it running. wondering if we're gonna have to actually look into what the program is doing. But we want the very first output to be 2. Did you import count from somewhere? Yeah, count is ITA tools. Hang on, let's stop this. We can start from a higher number. Let's just start from there. Don't print as much. I don't know if this is gonna get us anywhere. Should we try at least the test case so we know if this sort of works? So we got as far as that. Let's make a note of that. $117440 is what we're expecting for this example. $117440. Okay. Okay. Suppose I can leave it running while I think. All right. What the heck are we doing? 117,000 is roughly what would, okay, so if it was just outputting random programs, the chances of it getting right would be something like, so these are 8-bit numbers, so it's going to be 3-bit numbers, so it's like basically 1 in 8 to the power of, for the test example, it would be 1 in 8 to the power of 6, I suppose. Roughly. I mean, it could terminate early or something, so 8 to the power of 6. It's about 260,000. So that's about, yeah, that's about right. The number of values we're trying for A is roughly the chance of it outputting by chance. So it's almost like it's just outputting a random output each time. So in our case, it's going to be, God, yeah, this is too many, isn't it? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Eric suggested that a 3-bit number is a thrumber. Where did he say that? So 8 to the power of 16 is massive. Of course it is. Another stream earlier, I see. Alright, we're not gonna get anywhere with this. So So we need to start looking at what the program actually does. Like, at the very least, we need to make the first number 2. See what we have to do that. So at some point we need the operand. To be the number 2, right? That's the only way. Oh, no, these could be A, B, or C. Could also be 2 modulo 8. Alright, stop this program. Oh, man. Okay, so if we... Let's go to bed. I'll start with a new sheet of paper in the morning and try to get this done. Alright. See you next time. Guess we just have to follow this program along and see what it's doing. Or can we... Alright, let's just follow the program along. Get some idea for what's going on. So we've got 2, 4... Yeah, I guess I might actually have to write some notes as well on paper. I reckon even if we find the value, if we try that value, I reckon it won't even run in time. This is a case where we have to find, in theory, what the value of A is, but we're not necessarily actually going to run it at that value. I have an idea. Let's just see when we get 2 at the front. I want to know how often that even happens. Just that. If we find cycles here, then we're done. Like, it's just like the lowest common multiple of a bunch of cycles. Let's just try and see if we can find any cycles. But that's assuming a property of this program. But yeah, okay, so 2. So if output 0 equals, let's just say program 0, print a init. All right. Let's have a look at these numbers. Do we think it's actually cyclic? 17. Wait, what am I printing here? Yeah. 17, 81, 86, 94. Don't know. I don't see any real pattern here. Should we try printing that 17 to 81 and then... There's a big jump there. 50. So it's not... So that goes up by 8, that goes up by 4, that goes up by 4, goes up by 1. Then we go up by 7. 1. 7. 8. 8. 8. 10. Yeah, no. Okay, this is it's not gonna be cyclic, is it? All right, start running the program then. So we've got 2. And 4. So that takes us to BST. So, B equals get combo operand of operand percent 8. So we've got 4. Get combo operand. So it's A. So B equals A percent 8. All right. So B is now A percent 8. Let's say A starts with small a. So it's small a percent 8. All right. Then we go to the next instruction. 1, 2. So that's BXL. B equals B XOR operand. The operand is 2. So it's now A percent 8 XOR 2. Fine. Then we go to next one, 7, 5. So that's opcode 7. So the get combo operand is going to be B. So we've got C equals A divided by B. C equals A divided by 2 to the power B. Alright, this is already a mess. Then the next one is 4, 7. So that's this one here. B equals B and C. This is not gonna get me anywhere, is it? 4, 7, then we go to the next one. Then we go 1, 3. B equals B with operand being 3. Alright, so that 3. Now that's interesting, because when you got XOR... Whatever. Keep going. 1, 3. Then we go to the next one. 5, 5. And then here we output get combo operand %8. Operand is 5. It's B. So we want B %8. So I have the formula for what B will be at this point. It's a horrible formula though, and I don't see what I can do with that. What's interesting though, every time you add 8 to A, well, no. I have no idea what to do then. This, okay, forget running through the instructions. This just gets us our horrible formula, which you can't find a period or any kind of pattern with A. What else can we do then? Do we want to... look at when it um So after 5, 5, we've got 0, 3. What does that do? A equals A divided by 2 to the 3. So A divide out by 8. Well, that's interesting. Hang on. So that's the only time A changes? Okay, that's important. So A divided by 2 to the 3, 8. Then we go to 3, 0, which is the jump. If A is not equal to 0. So when A is 0, we finish. And we jump 0. IP equals... Jump back to the beginning. So this is... okay, I'm starting to see a bit more structure here now. It's actually... We're not jumping all over the place. We're actually always jumping to 0. Hello G12345. I'm doing this too. Yeah, this is stumping me a bit. But okay, I think I'm starting to get somewhere now. So we get the only jump command is at the end, and it jumps back to the beginning of the program. So it's actually much simpler than I thought. So if we want if you want exactly that many outputs, then basically we want to that sets bounds on what A can be. Hang on. So if A was... So there's 16 numbers here. Hang on. So we output a number, and then A divides by 8. Okay, so if A was, say... 8 to the power of 16. Then we would output a number, and then it would drop to 8 to the power of 15. Hello, DIJ. We got a difficult one today while we're doing int code stuff, assembly language stuff. Trying to investigate what this weird program is doing. So are you on part 2 now? Yeah, I'm on part 2. Just making some notes here. So if A was 8, 8 divided by 8 is 1. still isn't 0. Okay, so it's until it drops below 8. I see. Stew Squared, thanks for the raid. Oh, it's going alright. I'm at a bit of a tricky step with this part 2. Trying to work out I'm sort of now realizing that I can sort of set some bounds on what the value of A has got to be. It's going to be roughly... A has to be something like 8 to the power of 16 or something. Well, hang on. Let me just write this down. So, if A was 8 to the power of 16, we would output 1, output 1, output 1, blah, 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 blah. Then it would drop to 8, and then we would output 1, and then it would drop to 1, and then we output 1 more. Alright, so... I think we know that... Let's make some notes here. A would have to be less than or equal to it has to be strictly less than 8 to the power of 16. If it's 8 to the power of 16, then we get 1 extra at the end. So it has to be strictly less than 8 to the 16. And I suppose it also has to be greater or equal to... 8 to the 15? Is this right? Alright, well that gives us a bound, but that's still a massive range. I mean, I could try starting right to 15. That's not going to work, is it? 8 to the 15. Alright, try that. Hang on. We don't want to do that. Yeah, that's going to take forever. What's 8 to the 16? It's going to be 8 times bigger than that, so... Alright. That's one thing we know. A is between 8 to the 15 and 8 to the 16. Now what? Can't think what else to do. This is so confusing. We know the bounds for A. That will get us the exact number of things to match the program. But we need every outputted thing to match now. So we've sorted out the jump condition. That's fine. It's the output condition, which is the 5-5. This outputs B modulo 8. And B is like one horrible number. What do I do now? So B is essentially something like A modulo 8 that bit XOR with 2 XOR with A divided by 2. Oh god. It's a horrible string and there's no pattern to it, and I don't think, and then the whole thing is modulo 8. So we have the formula right in front of us. When we jump back to the beginning, we go back to 2, 4. B equals get combo, so it's going to be operand %8. So that's 2, 4. 4 is A. Alright, so B resets. So we've actually got the formula in front of us, but it's horrific. B... But then maybe there's some... Okay, this is what B looks like when we're outputting. A %8 XOR 2 XOR A divided by 2 to the power of A %8 XOR 2. There's also XOR 3. Well, this is interesting. Can we simplify this? If we're XORing with 2 and 3 and... Wait, what's 2 XOR 3? It's 1, isn't it? So that simplifies to 1. So XOR with 1 just means you flip the last bit. And then that whole thing, we want %8. That is what we output. And then A gets divided by 8, and then we do it again. So, and we basically want to output these numbers here: 2, 4, 1, 2, 7, 5, 4, 7, 4. So that's the formula basically. Okay, this is taking you a while. Well, have you done it already, Amara? I mean, that formula is complex enough that I don't think there's any period or any pattern here. Is it not just... we want to compute that formula... Alright, let's try... It's just that. But it's the same complexity as just running the program, isn't it? We're not doing anything crazy. Another raid. Everyone's raiding me at the worst bit. Thank you for the raid. Tomatoes cannot be trusted. I'm trying to figure out what the heck to do with this this part 2. This is kind of ridiculous. It looks like it just comes down to this formula right here. We want that. Are you close to solving the problem? I don't know. Guess we want to work backwards. Start with the right hand side. 0. And say, when A is at its smallest, we want that formula to be equal to 0. And then go... What does it mean to divide by 8? That's a bit shift, isn't it? A bit shift of 3. That's quite key, isn't it? Because that means we are actually looking at groups of 3 bits in this number A, and it's somewhat independent. So if we can but then it's not, is it? Because when you use this formula, such a weird formula. I can't wrap my head around this. 2 to the power of... And so what we know is we've got basically 16 values of A, and it starts off the first value is going to be A, then it's going to be A divided by 8. And A divided by 8 squared. And so on. And then the final value will be A divided by 8 to the 15. That's basically our values of A's. In each case, B would be that. And we want that to match these numbers. So the only thing that's bothering me is that I mean, it would be nice if each of these, so each of these is a bit shifted 3. So it'd be nice if each group of 3 digits in A is somewhat independent here. I don't think it is though, because that formula, I feel like it just involves all digits. Well, no, 8%. Well, that just involves, these just involve the last digits, but then this. Alright, Stu. Have a good night. This bit here. Maybe I should just try it then. So we just want to say, just assume the groups of 3 digits are all independent. So we'll say, so this is basically the first 3 digits of A after all those bit shifts. So maybe we can figure out what the first 3 digits should be. I mean, it's probably going to be 351, isn't it? Let's see if this theory holds somewhat. So when we get there, we get... Wait, no, this is decimal. We're talking about binary here, aren't we? Okay, fine. We can work out what the first 3 binary digits are. So for K in range 8, I want to see what these values are. K, and then here we've got. It looks like I've written this in a way that it will just work. So it's going to be K percent. Well, K percent 8 is irrelevant. K 2 to the power of K percent 8. Let's just try that, I don't know. 0, 1, 1, 0, 2, 1, 3, 3. Is the result supposed to be such a large number? Yeah. Because if you want to output that many things in your output, and A divides by 8 each time it outputs something, then it would have to be at least 8 to the power of 16 or so, 8 to the power of 15. Alright, so looking at this. 10135476. Okay. So that tells us we want the first 3 binary digits to be 001? Wait, no. What am I doing here? Yeah, 001. We want the last output to be 0, so the first 3 digits should be 001. I don't even know if I've written that formula correct though, but let's assume that's right. So let's try so let's say we've got a number 001 and then 000. And the rest is zeros for now. How many of these do we need? See, one of these groups for each of these numbers. So it'd be 16 basically. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in theory, we're starting from that number and working our way up, but maybe we can work out what each of these are individually. But let's try this then and see if we actually get zeros at the end. So starting number equals, so it's going to be like that. We'll have to just make a method which turns our groups of zeros into a... And then we need to do... I don't remember how to do this. Hang on, I need to look this up. Python convert... Well, that's got to be a string. Int. We don't need to convert it to des, we just need to have it. Okay. You just have to put 2 here, right? Start equals that. Let's try that. So we just go ahead, make the program. Skip this step here. Print. I want to see the output. Alright, try running that. Stop. They're all zeros. Okay. So with 3 digits there. So is that the process? Yeah, but then... I see. Now that we know that... Oh, man. Okay. I think we can probably put together an iterative method for cracking this then. So we need... that out. So we know... Let's just wrap this up in a proper method so I'm not typing it out. So we know that the out puts I don't know, just call it num out for a given value of a is this formula here. Okay. So get rid of this. Okay, so our a, call it our, is going to be none times 16. I'm just hard coding numbers for now. We can make it adjust to the program. It can't adjust to a general program though. This is very reliant on the way this works, so that's fine. R equals none times 16. So for I in range 16, we're working backwards from the program. So we're saying we've got A divided by that amount. So it's going to be the first n digits, but we may have already filled in some of these. So So our A string, let's call it A string, is going to be let's just take the first few things from arrow. So it's going to be join arrow from up to including I. So initially it doesn't use any of them. Plus 0, 0, 0. So that's our A string. So for A in range starting from so it's going to be starting from int A string and ending on int. So this is, so we need so B plus that. What's wrong with this? Okay. What? Should be fine. It doesn't like the nuns. Whatever. Oh, I'll tell you what. Let's just put empty strings in here. Then we can just do this. So as soon as we put things in, this will now have things in them. Okay, that works. Okay, so we range from 0, 0, 0 to that. Plus 8. There could be multiple. Oh man. They said the lowest positive integer, so we've actually got to find the lowest value. There could be multiple different A's which actually give the num out to be what we want. Okay. If num out of A is equal to program -1 minus I, right? So we start from -1 and work backwards. Then this A is the one we want, so we want to break here. There should always hopefully be 1, otherwise we're kind of screwed. That tells us what the 3 digits are to add here. So array I equals suppose we just have to take turn A back into binary and then take the last 3 digits. Okay. Is that it? Does that do anything? Aim range int a string 2 int a string 2 plus 8. Oh god, what have I done here? Why is there B? Ah, I see. We need to strip the B's off when we put Oh, it's because to begin with, there might be... Whatever, just do this. Initially, there might be 0 because the leading zeros were stripped away. Alright, off the smaller number, so then the 0b slipped in. Alright. So that's a thing. Let's test this. I have so much in my head, I can't, I need to release it. This is really, really confusing me so much. Okay, let's just say that. At some point I'll have to clean this up and make it into a nice neat program that actually does things in the right order. For R equals that, start equals int, so it's going to be 0b plus so we think start will work. Wait. What is this? Oh, that's printing all the outputs. No, those are all wrong. Oh, no, they're right. Up to... So 3305... Man, what was the first one? It was a 4. Alright, we're slightly wrong. We got those digits correct, and then... got a 4 instead of a 5. Something was wrong. Oh... It's because it's getting rid of the zeros, isn't it? So sometimes we need to pad. Hang on. So we find the value of A. That's an int. It's binary A. Alright, let's just... So we take binary of A. That gives us a binary number. Strip off the beginning thing. Okay. Then we get the remaining digits. And then I think we want to pad it. So how do you do that in Python again? Python pad with leading zeros. There's probably... better methods for well, Z fill. Left pad any string with zeros. Okay, there we go. That's what we want. Z fill 3. Better? No. Because we didn't do anything. Alright. Let's just pop this. So we get the array now. Okay, we do that. Do that. Array equals that. Print array start equals that. And then, okay, let's just see if that does it. What's this? What is this? What am I printing now? Oh, I printed the output and then... Alright, it's just... Well, it's not breaking out. Can we just... Okay, print output and then break. I just want to see what's going on here. What is this? I don't think I've used the array correctly. Print the array then. What is... Oh, okay, this is wrong. Oh, because I didn't use the last 3 digits. So it's a growing number. There. Okay, that looks like a nice clean array. Alright, 0, 3, 3, 0, 5. Oh, we still got 4. If num out a equals program -1 minus I. Break. I don't even know if I've written this correctly. This was just literally scribbled on paper. 4 is better than 5, I guess. Well, it's not, because it doesn't match the program. Something is wrong here then. This should be matching. Num out a... I don't even know if this formula is correct. Maybe I gotta work it out again. I don't know how many things we need to bracket here. Let's bracket this. Not okay, so I don't think 2 XOR 3 is 1, isn't it? Should I just put the 2 and 3 back in? 8%, 8. Oh, this operation probably isn't correct. I need to do that. Wait, what? %, 8. The second 8%, 8. Oh yeah. Didn't put nearly enough brackets here. Oh yeah, that's all wrong. It's doing 8 to the 2. I'm surprised it even got those digits. Alright, well, still. Maybe that was the correct order of precedence, but still. 2 to the power of... Pretty sure we don't need to do this, but let's just do it anyway. So we're getting 4. So, alright, when we get to that digit, so that one is this, that one is that one is these 3, this one is these 4, this one is these 5. Okay, I see. We're never actually finding something to make this 5, so it's just, this for loop is just... Okay. In that case, I see the problem. There may be... multiple. There may be multiple values that will make this work, and the one I chose just wasn't right. Oh God. Right. So then you would have to have some sort of search algorithm. Can we just do it by hand? Can we just say Alright, let's just go through these one by one. Just fill it in by hand, see what happens. Okay, so this one is only 1. Okay. And then here. Just say it's this. Seven and 6. Wait, no. What's this? What are we printing? Can we just turn this off? So immediately we don't find anything which matches. No, but we must have, because we did it before, didn't we? Oh, damn it. We're not starting the index correctly. Like that. Are we not? So we don't find anything to make this 3. But we did. I don't think this formula is even correct, probably. Whatever is happening here is probably not matching this. Oh, maybe I have to go work out this formula again. Wait, so what did I get when I originally ran this? It was 16. And array was... And then we did break. We've got 0, 0, 0. Why did I not get that now? 0, 0, 1. Oh, that array was wrong. Yeah. Why did I have 1, 1, 1 there? We got 0, 0, 1. We know it's 0, 0, 1. Okay. Alright, let me see. 8. It's just 8. Okay. So go 1, 1, 1. And then 2, 3. Now it doesn't find anything. Wait, what did we get last time? Eight. Print A. Wait, 8 means... That's the full number. That's okay, fine. I mean, we don't really need to strike this number. We could actually just use the program itself. I don't understand how I got so many matching numbers before. Yeah, I guess the explanation is this probably doesn't actually match the formula, does it? Let's try working this out again. So 2, 4. Okay, so we start at 0, 0, and A. 2, 4. 0, 0, A. So 2, 4 is BST. So 4 is A. So B is 8%. Okay. Alright. Then the next slot is 1, 2. Operand is 2. Alright, so we do that. XOR 2. Then we go 7, 5. CDV. So C is A divided by 2 to the power of... So we've got 5. B. A divided by 2 to the power of B. Okay. A divided by 2 to the power of 8%. Okay. Then we've got 4, 7. So B equals B with C, alright. And we don't use C again, I assume. 1, 3. So all of that goes with 3. And then 5, 5. So we take B modulo 8. So all of that modulo 8. Alright, does that match what I've written? %8. Let me just write it in order because then I can check it easily. So we've got 2, and then here we've got A divided by 2 to the power of 8%, 8 XOR 2. And then XOR 3. No, I don't know. Wait a minute. 8. If it's 8, it should be 0, 0, 0, not 1, 1, 1. Why did I... Oh, no, that's because this is not breaking out. So we're saying 0, 0, 0. Oh, maybe I made a mistake earlier. Okay, go on to 2, 3. $67 and $70. Here's where we've got two things. So before we went with 67. We'll carry on going with 67. I just want to see where this goes. So break. Zero, 1, 1. Okay, we're going with 0, 1, 1. Alright, let's just go 3, 4, 5, 4, 1. Okay, so that's 1. One and 1. And then we've got 2. God. 4, 3, 2, 9. Is there a way we could know which one we want? Alright, 4329. Go with 4329 then. This is probably the one which fails. I could just write some sort of search here. That would be the sensible thing at this point. Because it's gonna keep branching, isn't it? Alright. Let's try and finish this off. Let's say, oh, I just want to investigate further. Alright, just keep going. I just want to see what it looks like. It's going with 4329. So that's 001. Okay, let me go to 5, 6. And then we got nothing. So let's go back. Four, 5, take that out. Oh. Well, I suppose we just have to hack this in. Say A equals 433. Alright, G 1, 2, 3, 4, 5. See you next time. Enjoy your walk. One, 5, 6. Well, now there's 2. Go with this one then. 001. If it branches again, we're just gonna have to go back and do a search. It is gonna branch again, isn't it? And now we've got 6, 7. Yeah. Well, we've not hit a wall yet, so we can just keep taking the smallest one. So when do we actually hit a wall? So we get 0, 0, 0. Okay. So we've got that. 0, 0, 0 again. Okay. So far so good. 1, 1, 0. $101. Alright, we're not hitting any problems yet. Can we make it to the end? Yes. 001. Okay. 011. Mm-hmm. 110. 010. Fuck. And then we're stuck. Or if we just backtrack, maybe we only have to change the last one. So that's what we had. What else do we have? There's 3. Let's just go with the next one then. So going with 101. Now we go 14, 15. No. What did we have? All right, go with this one then. Ah, what have I done? Oh, okay. Break. Wait, what am I doing? Okay, we're doing that. So it's 111. Wait, what? I think I've screwed up somewhere. Hang on, hang on, hang on. Also, what happened to the music? Which one am I on? Alright, just get rid of that. Print these out again. 13, 14, is it? Yeah, okay. So that's the one we want. So we take that one. Okay, so we do use 111. Okay, fine. Getting close. I don't know. But I don't think this is gonna work. I think they've made it so that... Right now what? Go 14, 15, 15. Okay, okay. Zero. This is so stupid. I shouldn't be doing this by hand. At this point, this could have easily been done by code. All right. 110, and then what? 15, 16. All right. Is that gonna work? So we had to do manual branching because I couldn't be bothered to write a search. Or like just, it's not a search, it's a, well, it is sort of a search, but it's a search where we're making sure we increment, like lexicographically, whatever. Alright, let's see if this works. How did this method become so complicated? Alright, so do that. that. Two 412 754 713 550330. Take that out. That's the A value. Alright, if this is right. I mean, we're there, right? But it might be one off or something, but we're there if we've actually managed to get it to print the program. Yeah, it's correct. Oh god. That was a mess. And now I know there's gonna be some far easier way of doing this, but I was just so stubborn on continuing that manual process. But yeah, I mean, that would work if I had just, instead of doing that manually, I could just, it's basically backtracking, so you go back a step and go to the next viable thing and so on. So for each, instead of breaking here, we create a list of the potential A's. Yeah, you can write this recursively. In fact, yeah, it would actually be quite clean if you write it recursively. In fact, why didn't I do that to begin with? So you want to get... Anyway. I don't think you could really write code that would solve the general program. That would just be absurd, because they could be doing any kinds of jumps and any kinds of things, so... I mean, other than increasing A from 1. But then how do you detect infinite loops? Well, you have to check for states, repeated states, and stuff like that. Anyway, the program was much simpler than I had concerns about, but... 14 minutes to solve that one. Oh, sorry, I've got the browser open. Let's see who's done it. A few people have. Alright, now some steps I could have improved. Okay, one is, yeah, write that backtracking thing recursively. The other is don't bother writing out the big formula with the modulo. Just run the program on a given A. So just eliminate, you want to eliminate the jump. You could literally just cut off the jump condition from your program. And then you'll have a program which outputs one output, and that is basically that basically replaces that. We don't need that. Or we can redefine this as program without the jump at the end, and something. Yeah, that's it, isn't it? It's just program minus the jump and run it on A and 0, 0. So we would actually just have to modify. run... We don't have a run program method. I should have made a run program method. And that can take in a program. That would make more sense. Yeah, I don't really... see how we can avoid this backtracking bit. Alright, no more thinking. Let's just stop there. That's been 2.5 hours. Alright. Oh, I imagine there may well be some people still on this. Let me check. Scally Games Dev. And then it's lots of Call of Duties, of course. Alright. Is this day 17? Yeah, okay. Alright. I need a break now. Can go watch Scally Games Dev struggle. I don't know if they're struggling. Thanks for watching and see you tomorrow for problem 18.